Hello, people. I hope you had a good weekend. Maybe a little miniature spring break, hopefully. I have a question. I'm just curious. Like, what is people's threshold for days without a shower at this point? Um, so please put into the chat the answer to this question. When a person has regular access to a hot shower, at what point is the maximum days that they could go without a shower before it's just too gross and they just really need to not continue? So how many days is that? Please put that into the chat. And if you ever come in late, please just put something into the chat if you're not sure what the question is, so we can count you as present for the day in the class. Okay. All right, I moved homework 6 to Thursday because that way we can have homework just regularly due on Thursdays starting again this week. Excuse me. And I had some people asking about homework 6, problem 6.6. So I'm going to try to clarify that a little bit right now, just in case people are not sure what's going on. So this is on page 171 in your book. And this is asking for a boundary of rejectability. That's what this question is asking you to come up with. So basically, it's asking for a range over which Chauvenet's criterion is either met or not for the different numbers of n points. Like n is changing. Like let's say there's 5 measurements. What's that range going to be of Chauvenet criterion validity compared to if n equals 10 or if n equals 15 or n equals 20 and so on and so forth. So hopefully that helps. It's strangely worded. And several people have asked about it. So. Any questions? Okay. I have a question for you. What is curve fitting? What does that mean? Curve fitting. And why do I care? Maybe that's more important. Why do I care about curve fitting? And what is it?
It's like some kind of equation that is attempting to describe a trend with the data, with some kind of data set.
Okay. Yes.
Specifically, a trend that is represented by a curved line or a parabola or exponential as opposed to a linear fit.
Okay, yeah, any of those. So like some expected behavior mathematically from our data is when we would do a curve fit. So why do I care though? As a physicist.
It allows us to easily describe what's going to happen based on like former measurements. So like with like kinematics as an example, like G isn't actually 9.8, but we figured that out probably from a curve fit of a whole bunch of data points that we took from like dropping stuff. And it gives us something convenient that we use for our kinematics equations.
Okay. We could have just done an average though, right? To find G with all those data points. Why do we do a curve fit and not an average?
The curve fit offers a different way of finding uncertainty, right? Because you can find goodness of fit in the R squared, So you can see how well each type of fit describes the data. And you can also figure out uncertainty, and you can do future projections for what's going on in different systems, like with COVID. I did a project on that in linear algebra.
Okay. So, anybody else? Did we miss anything about why we care?
I think Sam pretty much said this, just in different words. But when I think of it, I usually think of like extrapolating, like using it to extrapolate what could happen with a value that's not in the table.
Okay. Great. All right, anybody else? Okay, I think we have a pretty good, sorry, my mouse situation is weird right now. I think we have a pretty good basic understanding of what curve fitting is and why we care, but we're going to go through this just in case. This presentation that I've put together, and we're going to do some curve fitting on Python today. So if you want to do that along with me, get your Anaconda software ready. All right, so what is the goal of curve fitting? Is the question I asked you last time. And the goal of curve fitting, like when you sit down to write a curve fitting program and you need it to like complete its job and give you some kind of result, what it gives you is called the fit parameters. Okay, so what we're trying to achieve when we do a curve fit, like as far as computationally, is we get these fit parameters out. So let me remind you what those are. I think you know what they are. You've done this in lab, but let's just go through this example anyway. So let's say we measure the speed of light. This is an experiment in senior seminar where that you might have seen them in the hallway recently with a laser, and they have a detector and they have a laser, and they shine the laser at a mirror, and the light comes back to the detector with a square wave, like making the laser happen and telling the detector when to measure. So they measure how long it takes that laser pulse to go down the hall and back with a detector and an oscilloscope. So I made up some data here. And they're doing this as a function of distance. They move the mirror back to different distances and they measure the corresponding amount of time it takes for the light to travel there and back. So I made up some data for some arbitrary distances. These are in meters and this is in seconds. And I calculated a speed, a corresponding speed of light for each of these rows. It's kind of tempting to calculate a speed of light for each row because we've done that a lot in our history of school. And then we take an average of all those individual speeds of light that we measured for all those data points. But like as Sam was mentioning, we can get more information if we do a curve fit. And not only is it going to be more information, it's going to be more accurate. Because a curve fit is going to take into account all the points together at the same time. All the data set is considered at the same time instead of one data point at a time. Okay, so we have here our list of data points on the left, and I put those into Python and did a fit of those data points. And we can see that we have our points shown here, we have our curve shown, and here's our equation for our curve. So the slope here, 2.8109 e to the e8 meters per second is the slope, which is going to be the speed of light. You can see there's a pretty big difference. We have 2.8109 here and 2.912 times 10 to the 8 meters per second. So our average and our fit calculated speed of light are very different. And that's because our fit calculated speed of light is going to take into account all the points kind of at the same time and find the best number here considering all of them together. So anyway, we also get this bonus information, a y-intercept. And that is useful, even though we don't really need it for calculating anything, like for verifying the speed of light, it's still useful. Because it is supposed to be 0. Because, right, v equals lambda f, sorry, or d equals the speed of light times the time. So there's no plus anything in that equation for the speed of light. It's just the speed of light equals the distance traveled divided by the time it took. There's no plus anything. So we would expect this y-intercept here to be 0 for our situation. There shouldn't be like a plus something. So that gives us some information that there's some kind of offset happening of our entire plot where the points are not lining up so that the intercept is 0. So maybe we can get some information about what our equipment's doing, knowing that that y-intercept is not 0. Okay, I'm going to go into some more detail here. Just wanted to give you a quick sort of intro, and then make sure you understand this word or this phrase, fit parameters. The slope and the y-intercept are what was actually calculated here. Those are our final bits of information that we are getting out of this curve fit. Those are the fit parameters. The goal of curve fitting is to achieve all of what I've just said, but ultimately we're trying to get these two numbers, in this case for this function, y equals mx plus b. We want the slope and we want the y-intercept. Those are our fit parameters in this case. So that's what fit parameters are. And guess what? There's a FET for curve fitting. That means we can simulate a curve fit and watch what's happening as we change things around. Okay, here we go. Alrighty. So we have a little bucket of data points down here, and they have get this out of the way. They have default error bars. So we're gonna like just disregard the error bars for now. And we're just gonna look at the points, and I'm just trying to make something linear looking here to have something to fit. So let's pretend we did these measurements. Okay, there's our measurements. If I click this, I can add a fit to the set of data here. And what I get out of my fit is the fit parameters. 1.2 is the slope, and 1.8 is the y-intercept for this random set of data that I just made up. Okay, yeah, so this is, we've already kind of ahead of time looked at the data without the curve there, and we see that looks like pretty much like a line. So, and we know that when we took this data, let's say it was the speed of light experiment, we know we should expect a linear outcome. So we have chosen in this case the linear y equals mx plus b function to do that fit with. So we are going to get m and b back whenever we choose linear as, or to do it when we choose the y equals mx plus b as our function that we're predicting matches up with the data, which is what Sean was talking about. You get some kind of equation that correlates to data, and you kind of put them together with the fit, and out you get these fit parameters. You find the slope, you find the y-intercept. And then you can get information like chi-squared and r-squared to tell you how good of a fit is that. Is it a crap fit, or is it pretty good? R-squared is more about, is it linear? And x or chi-squared is more about how far away are the data points from the curve. It's probably best. Thank you so much. All right, any questions so far? Y'all already knew all this? You remember all this from intro, lab? Kind of. Maybe not. Okay. Well, that's why we have this class, to make sure we are learning this stuff. Okay, so there are lots of different ways to do a curve fit, different algorithms to find the equation, or to take that equation that you expect is going to work and then apply that to your data. There's lots of different mathematical approaches to that. And the one that is the focus in your book and what is very commonly used by a lot of people is linear least squares regression. All right, so you perform an experiment and you're measuring two different quantities for each data point, like the speed of light one, where we were measuring distance and time. We were measuring time of flight and distance traveled of those photons, of those pulses of light. So that's two different quantities for each row of my Excel spreadsheet. It's natural to then plot those values one versus the other. And often those are linearly related, those quantities in physics. So here's an example of a whole bunch of data points that are meaningless, just random data points, but obviously linear. And then there's a linear least squares regression line or curve placed in here so that it's basically the minimum distance away from all the points. That's how it's done. Anyway, so when that regression happens, we determine the slope and the y-intercept of that line that gives us the best fit. And then those fit parameters, A and B, and their uncertainties, delta A and delta B, are the pieces of information that are important for us to get out of this curve fit. Okay. Notice I am leaving off error bars right now on purpose because there is a linear least squares regression for just points, and then there's a linear least squared regression called a weighted linear least squares regression for including error bars as part of the mathematical calculations. So right now we're just talking about without error bars, like the simpler method first. All All right, yeah, so there's different computational methods to determine the best fit line. One way is to collectively minimize these distances of the points away from the curve. And they could be like perpendicular, they could be straight up and down, they can be perpendicular to the curve itself, whatever. In this way that we're describing here, we're talking about all of the y distances. So if we take each point and measure how far it is from that blue line up to the point, those are called the residuals. And we want to add all those up and minimize that. We want that to be the smallest thing possible. And then that way, the curve is closest to most of the points. It's going to fit through most of the points the best way. Okay, when is it okay to use this linear least squares method? Well, it does actually depend on the uncertainties of our y independent or dependent axis points compared to the uncertainties in our independent axis points. Even though we're not showing data points right now, sorry, we're not showing error bars right now, we still need to know about the error bars because the ones in the y direction should be much bigger than the ones in the x direction for linear least squares regression to work. I wrote that backwards on the slide. Be negligible. Yeah, sorry. What I said out loud was correct, and what was on the slide here was backwards. Yeah, okay. I think we got it now. So the uncertainties in this direction need to be big compared to the uncertainties in this direction. Your x-axis uncertainties should be really small, should be negligible compared to the y-axis uncertainties. Okay, so that's an assumption of the linear least squares method. So if we have a set, like a column of points like we were looking at here, let's say the time, well, in reality, the time uncertainties are going to be really small compared to the distance uncertainties because an oscilloscope is going to do a good job of measuring these times, and then a meter stick is not going to do a great job of measuring these distances. So we know in our case that the time is going to have a much smaller percent uncertainty compared to the distance for our data set right here. So we did put the time of flight on purpose along the independent axis here on purpose. And we put the distance traveled along the y-axis, the dependent axis, which is kind of backwards from what you might do from looking at the table here. Usually we take the thing that we vary with control and put that as our independent variable. Like normally we would like kind of have a instinct to put this on our x-axis. But since we know our time measurement has a really small percent error compared to our distance measurement, we put the time quantity on the independent axis on the x-axis and the low precision quantity on the y-axis, on the dependent axis. So that was on purpose. So yes, the uncertainties need to be bigger in the y direction than in the x direction, and hopefully a lot bigger. Now, we get to talk about the math. Oh, goody. So, we're going to first find the residuals. Let's remember what that means. Go back to here. We have these data points. Each of those is x sub I, y sub I. Okay, so we have n data points, and I goes up to n. When we count from I to whatever the max is, that's going to be n. And each of these points is going to have some distance away from the curve. We're going to call the curve y. And the data point y value y sub I. So that's what's happening in the math here. We have d sub I. We find d sub I, this distance, is going to be the distance between the curve and the data point, but just in the y direction. Okay, and we know that the curve is equal to, showing on the second row, the curve y is equal to a plus b x sub I. That's the y-intercept we're looking for. This is the slope that we're looking for. So the slope times x sub I of our curve, our line, is going to give us the y value on that line. Okay, then we can substitute or combine these first two equations, and then we get the second equation here. So a plus b x I equals di plus yi, and then we move the yi over. And that's that's the residual. That's known as the residual. So we're going to square that and add up all of those residuals. And here we have the residual squared. We have the sum of the residuals squared here. So once we substitute back in for d sub I here, we just are rewriting that, but in like a more expanded form. The residuals are going to be the y-intercept plus the slope times x sub I minus y sub I, all of that squared, and we add all of those up. So now we have a function of two variables. We want to find, in the end, we're looking for a and b. So a and b are like the variables that we are considering different values for as we go through this process. So a and b are like our unknowns, and we want to solve for those. So we have this thing as a function of a and as a function of b. And we want to find when that is the smallest. We want to take all those distances and find when the sum of all of them is the smallest. So we can take these functions and take the derivative of the function with respect to a, and then with respect to b, and set that equal to 0, and use that fun trick to minimize our function, to find those minima of these functions. Okay, so we continue this on the next page. The partial derivative with respect to a of that sum of the squares. Sorry, getting this out of the way. Is going to be equal to, we're going to pull this 2 down to the front, and then keep the inside of our function there, and then there's nothing else like attached to the a here, so we don't have to multiply any more chain rule sort of things outside. So we end up with 2 times the sum of a plus b x sub I minus y sub I. The sum of that is equal to 0. And we can come up with this expression that describes the minima of, or the minimum of our function of a and b. And then we repeat the same thing, but we take the derivative with respect to b this time in step 2 down here. And b does have a constant value here next to it. So we multiply that on the outside as part of the chain rule, but otherwise it's the same steps as before. And we end up with this expression for when we consider the function minimized with respect to b. So these two are called the normal equations after we have simplified them and gotten them into these two states here. We take those two equations because we basically want to combine those two equations now and solve them for a and b. We have two equations and two unknowns. X sub I and Y sub I are data points, and n is the number of data points, and then a and b are the unknowns. So we want to combine these two equations and solve them. So it makes sense to do that with a matrix. This is exactly what linear algebra was invented for. We're going to take those two equations, here they are rewritten on the slide here, and we're going to convert them into matrix form so that we can solve for a and b with well-known methods. Okay. Now, if you haven't taken linear algebra, don't worry, it's okay. Basically, what this does is allow us to just rewrite these two equations in this different kind of framework. And using this framework, we can do computations that are quicker than maybe without that framework. So what we're going to do is use Cramer's rule to find A. And it's just, you just follow an algorithm. If you have a matrix set up like this, where you have a matrix times a column is equal to a column, then you can solve for A and solve for B using Cramer's rule. So I have a slide here about Cramer's rule and why it's true, but let's just go through the algorithm here. So the way to find A using Cramer's rule is you take this matrix over here and you substitute, you substitute this column for the first column, and you put that here in the numerator. And then these lines here mean determinant. So that means that's like a special kind of operation you're going to do on your matrix and turn it into just an expression instead of a matrix. So that's the first step. You take this column, you put it in place of this part of your matrix, you rewrite that here, and then put these lines around it because that means determinant. Then you repeat that and put the same thing in the denominator, except now you replace, or sorry, we're done. I'm talking about B. So then you take the original matrix and you substitute, or you put that in the denominator with the determinant signs around it, because you're going to turn that into an expression as well, using Cramer's rule. So to find the determinant, you multiply these two quantities here, and then you subtract the product of those two quantities. So that's how we went from here to here by taking that determinant, multiply these, and subtract this product. All right, same thing for the denominator. We found the determinant of this matrix. We took these two and multiplied them together. And then we took these two and multiplied them together. And we subtracted this product from that one. And we get this expression here at the bottom, algebraic expression for A in terms of x sub I and y sub I and n. Like we have solved for A now. We have found that fit parameter. That's the y-intercept thing. Is that the y-intercept? Yeah, that was the y-intercept. All right, so now we do this for B. We also need to solve for B. So we use Cramer's rule to find B. So we do the same thing where we substitute for one of these columns in our matrix in the numerator. So we substituted in the right-hand column this time instead of the left-hand column. This is to find b. We find the determinant of this matrix in the numerator, and we have the original matrix in the denominator. We find that determinant. We find those determinants the same way, and we end up with this expression for b as a function of all known things. Not a function, as you know, for every sub I, you could find b. Okay, we also can find the uncertainties of our A and B quantities. But let me go back and just reiterate what we have done here by taking our data points and considering those data points and taking into account that we want to minimize these distances, these y sub I minus y distances squared and added up, we have been able to find an equation for the residual A and for the residual B. So here was our equation that we are assuming is the model for our data. So that's what we're using for our fit. And we want to find A, the y-intercept, and we want to find B, slope. And now we have expressions to be able to do that, be able to calculate those. Okay, I'm gonna stop for a minute. Questions, anybody? Okay. All right, now here's Cramer's rule. We're going to come back to the uncertainties in a minute. If you care, this is the definition of Cramer's rule. You can basically take your matrix M times a column vector R equals column vector P. You can find the column vector R by taking the determinant of M sub I divided by the determinant of M, where M sub I is the matrix formed by replacing the ith column of M by the column vector P. So that's what we just did. And if you want more information about Cramer's rule, we have a reference here on Wikipedia. All right, let's do an example. Here are 3 data points. 3 data points. Never would that ever be enough, really, for any kind of experiment. But it's really nice for a simple example of linear least squares regression. So we have these 3 data points, and we're assuming it's linear. Looks kind of curved to me, but whatever. We're going to assume it's linear and find the best fit line for these 3 data points. So it's going to be somewhere in here. Okay, we can do this on Excel. We can take the equations that I just showed, and we can put our x sub i's and our y sub i's, and we can find this distance y sub I minus a minus b x sub I, and basically follow the algorithm or the math that we just showed here to calculate B and to calculate A. And we can do that in our spreadsheet, and we end up with, again, we're gonna talk about uncertainties in a minute, or maybe next time. We find a slope of 7.8. A slope of 1.25 times x, negative 1.25 times x, and a y-intercept of 7.8. And those have some uncertainties there. So that's a way to do linear least squares. You can write your own code in Python to do those calculations. You can put this all in Excel. But typically we use, doing a manual sort of way, like in Excel, for very large data sets is tedious and unnecessary. So I want to show you an example in Python with some other data, unless we have questions. All right. Here we go. Okay. I'm going to need to restart Jupyter Lab. Hold on a minute. It's usually faster. I don't know. All right, so I am launching Jupyter Lab. And we should be able to see this notebook soon here. Here we go. Oh, great. Of course, I have a syntax error. All right, we can go through this one. So I put the data points into Python by making an Excel file that literally looks just like this. Maybe I can show that. Like data. Okay, so here's the data set. It's the same one I showed you earlier on the slides. I made up this data set. I didn't put the average in there. And I didn't include the speed. Okay, so I put this exact data set. I saved this file and dragged and dropped that file into this folder region of my Python interface and called it data.xlsx. So then I use the command that allows me to import data, and I use the command that allows me to actually import the data. This is like to import the library, and this is to actually import the data from this file data.xlsx. And so this variable here is like a matrix. And so I typed the name of the variable and hit run so I could see what was in the variable. And it shows me, just so I can check that it shows me the distances and the times, just like I thought it should be. Okay, and then I am now importing a bunch of libraries and stuff for plotting and for figures. And then, I'm sorry, here's a whole bunch of other kind of plotting, font size and formatting stuff here. I then take that matrix Excel underscore data dot distance. So Python assumes this word up here is the name of your column in your Excel file. And you can name a vector, like a one-dimensional vector, something, and then put that data in that column, Excel data dot distance, into this vector. So I call that D column, and for the time I call that T column. And then I do the PLT figure to get ready to plot a figure, and I put in, first I just want to plot the points. So I did a PLT dot scatter, T column for the X axis and D column for the Y axis, because I know my time is more precise. Okay, and then I did some formatting stuff, and I told what, font, axes, labels and stuff. I don't know how to put spaces in there, so sorry. Working on that. So there's my data. There's a random outlier here, which I should probably do Chauvinet's criterion on and see if I need to take it out, but I'm just going to leave it in for now. Now, to actually fit this data in Python, I could write my own code that does linear least squares regression. People did that this round in senior seminar and bragged about it, and we're very proud. So totally you can do that. Or you can use this function. There's a bunch of different functions you could use. This one, np.polyfit, uses linear least squares regression. And if you choose a 1 here, you're choosing a polynomial of order 1. So y equals mx plus b. So this can do more than first order linear least squared regression, but for now we're using it just for first order linear least squared regression. So we put our T column here as our x-axis and D column as our y-axis for the fit. And notice that it doesn't even like show me a graph or anything. It just gives me back my fit parameters. I just get my slope and my y-intercept. That's all I get back after I do a fit on Python. So to plot that, to show that, I have to build my own line to be able to show that now. So that's what I'm trying to show here. I'm going to zoom out a little bit. Okay, so there's that fit function that gives me the slope and the y-intercept of the fit for that data, T column, D column. So what I need to do now is create a whole bunch of data points to plot to be my curve. Because there's no Python function that I know of that will just plot that for you. So you have to kind of build an array and then plot the array. So I chose 100 points between 0 and the maximum on the x-axis, 3 times 10 to the minus 7 seconds. And in order to build that graph, that line, I created a corresponding y function array of the y values that correspond to the x values, using the slope up here as my m and using the y-intercept up here as my b. Then I again plot just the points. I do a scatter plot command with some font and font size stuff and naming of axes. And then I also plot the actual function, the fit, in red with this label, which I tell it to put in the upper right. So there's my fit equation in the upper right there. It shows my slope and my y-intercept. Python doesn't just do that for me, not like Origin. I have to build my own graph to show this in Python. I will put this code on the As You Learn page. So you don't have to like type all that. You just copy and paste and edit and whatnot for whenever you're doing linear least squares curve fitting when it's appropriate. Okay. Questions? Anyone? Okay. I'm working on the exams, grading them. I am working on it. we'll try to have them back to you ASAP. Okay, they look fabulous so far. I feel like I might have insulted your intelligence with questions that were not hard enough. Sorry. Anyway, have a great couple of days, and I'll see you Thursday. Bye, everybody.
Have a great day.
You too, thanks.